Okay, Joy Bells. I'm going to open up a worksheet and then I am going to do the problems and explain the process as to how we're going to move forward. So just give me a moment to get my screen. You know how I am with computers. I am challenged, but I think I'm getting there. Yes, I think this is what I want. Now I got to make sure that we're recording. We are, and I think we're set to go. All right. So let's get to the board. All right, so what I'm going to do is put a problem on the board. And as you're watching the video, pause the video, take as long as you want on the problem. If you know you can't do it, then just follow along with my explanation or get together if somebody knows how to do it. And that would be much better if someone knows how to do it there. It's very important to learn how to explain things to others. So do that and then watch the video. And you can always go backwards and forwards. And so this is just a smattering. This is actually a worksheet that I gave at the end of a semester in a pre-calculus class, probably 100 problems. We're just going to do the first 25. All right, and that'd be enough for you to get some good practice. All right, so the first problem I know we've done many of. So this one you try to do in your head without drawing it out if you feel comfortable doing that. Otherwise, if you're still learning the process, draw it out. So the cosine of minus 7 pi over 3 is what I asked. Okay, now I don't have to stop here at all. I'm just going to show you, the problem. So minus 7 pi over 3 takes us to the fourth quadrant area. We're looking at the cosine, so we're looking at, I believe, a half, but we'll draw it out. So there's your circle. Chunks of 3. So there's your first chunk of 3. You're going in the negative direction. Second. Third, obviously, minus 6 pi over 3 is once around counterclockwise or clockwise, which is really looking at the graph to the left of the y-axis. And so this is our triangle, right? And we can see that that is indeed a half. Cosine is width in the unit circle. This is just the unit circle. All right. So now, do I have an eraser? Yes, I do. Handy. So problem number 2. Problem number 2, tangent of the arcsine of negative 4/9. This way I don't have to think about making up problems. They're already made up on the sheet. All right, so you're pausing the video. I'm not. So the arcsine is drawn in the first or negative first quadrant. The arcsine looks at from -1 to +1. It's asking you for what angles are being generated. Okay, I'm not going to do this in a unit circle. I'm just going to take a educated guess at a -4 to 9 ratio. That's the sine ratio. And we're looking for the tangent, which means we need that location. So we got ourselves 81. We got ourselves 16. We got ourselves 81 minus 16, 65. So that's the square root of 65. Okay, and tangent is opposite over adjacent. So this answer is equal to -4 over the square root of 65. Okay, and if I'm multitasking here, trying to talk to you how to do the problem, and I lose my concentration and make a mistake, you can email me and say, hey, are you sure that's the right answer for number 2? Okay, number 3, secant x plus 2 equals 1. I'm sorry, equals 0. And we're going to try to solve remember the language now. This is not inverse, so this is an angle. We're trying to find the angle that works. And we need -2, right? So we really need a -1 over 2. But let's talk about reciprocals. The reciprocal of secant is cosine. Cosine of x is related to secant. I've always remembered it as in, okay, cosine, cosecant. Oh, it's a math class. It's not that. All right, so the secant and cosecant, you would think cosecant would go with cosine, but it doesn't. All right, so that's a little memorization tip. So we now know that secant x is equal to 2. And I'm going to write 2 as 2 over 1. That's a ratio. Okay, and what is the secant ratio? Well, secant is 1 over cosine. All right, and I'll do a shortcut in a minute, but anytime you have you know, in case we haven't talked about cross products enough, you know, 2/3 equals 4/6. 2 times 6 is 12, 3 times 4 is 12. So you can always do cross products, which is 2 cosine x. I'll take the shortcut in a little while. Equals 1 times 1, which is 1. So, oh, I made a mistake here. So that's negative, right? So -2. Forgot to put the negative in. I told you multitasking here. So cosine x equals -1/2. And now our brain goes to the unit circle. Where's -1/2? It's right there. So up and down and down and up. And we look at chunks of what? 3. 1, 2, 3. So the pi over 3 gets me 1/2 on the positive side. 2 pi over 3 gets me the -1/2. And so does 4 pi over 3. I really do want to start getting us a sense of radian measurement, a better sense, because I know how hard that is for students to finally grapple with and understand. Pi is 3.14 times 2 divided by 3. This is close to 1, right? So 2 radius lengths would be 1, 2, okay? Roughly. I want to get better approximations than that going forward. So I'm going to have to write them out and memorize them myself. That's why I like repetition. How long have I been doing this? 40 years? And I'm just doing that now? All right, so now we're going to take the shortcut. All right, so if this were my problem, I would say, okay, okay, 1/4 equals 2/8. All right, just some truth about fractions. Well, if 1/4 equals 2/8, 4 over 1 equals 8 over 2. In other words, you can just flip fractions that are equal, right? The reciprocals have to be equal. So what's the reciprocal of secant? Cosine. Remember, this is coming to this side. What's the reciprocal of -2? -1/2. So that could have been just without, you know, doing all that other stuff that I did, an explanation. Could have gone right here when you master this problem. And then you don't even have to draw the circle. Cosine, -1/2. Okay, second, third quadrant, bang, done. Okay. Doesn't hurt to get a quick sketch of the cosine curve. We want to become more familiar with it. So here's 1/2. I'm sorry, here's a half. And when do we get a half? That's a terrible drawing, huh? Way over here at 60 degrees. Right? When do we get -1/2? -1/2 would be about there. Oh, right about here, 120 degrees. That was our 2 pi over 3, and 4 pi over 3 is over here in the third quadrant. This is the first 90 degrees, the second 90 degrees, the third 90 degrees, and the fourth 90 degrees of ratios. Okay? Just trying to layer a little bit of understanding. And you can always replay what I just said a couple of times and try to make some sense out of it. All right, so what's the arc cosine? The arc cosine, I like this fact. I can just look at some things and go, oh, here's a question. So the arc cosine of, not writing that very well, -√3/2. Famous ratio. Okay, so hopefully, remember you're pausing. That came to mind. That's the arc cosine, which goes from the x-axis is the ratios. This is all about inverse operation. That's our ratio. So your input are ratios. Your input are ratios, and your ratios go from 1 to -1, and these are your angles. We want to go to -√3/2. -√3/2 is over here, and so that's an angle. So what's my angle? Over here, Jesus, I'm so used to drawing this backwards. I'm not on a coordinate system right now, just conceptually talking, all right? Because the arc cosine is a little bit more of a difficult graph to do at the moment, given the fact that I'm talking about it in these geometric perspective ways. All right, so how far did we travel on the arc? That's really what we're talking about here. How far did we travel on the arc? Hopefully you can see 150 degrees. Or 5 chunks of 6, 5 pi over 6. All right, so pi, 3.14. I want to keep doing this for my own benefit. This is near a half, So 5 halves. 5 halves is 2.5, 2.5 radius lengths. So there's a radius length. There's 2 radius lengths and a half. Okay. Remember, if we have an angle, we normally describe it with that symbol, but isn't that just part of a circle? So isn't that degree measurement also a part of a circumference? And circumference is 2 pi r. And if we're using the unit circle, circumference, if r is 1, 2 pi, 6.28, roughly 6.28 of those to go around. And that's the language of radian measurements. Okay, I'll put another problem on the board. You pause it. Let's see, I've got to get here. Okay, I can see it now. I gave you simplify. Simplify. 1 minus cosine squared x times cosecant x. Okay, so you copy that problem down and think about it a little bit, and I'll just do it because you're thinking about it. You're pausing the video. You have to recognize that if x is an angle, like 30 degrees, then this is the sine of 30 degrees. If x was 30 degrees, that's the sine of 30 degrees because you're dividing by 1. Opposite over hypotenuse. And the sine of 30 degrees we know is a half. Well, what if I change this to x? And then this to x, as in, well, that's true for every ratio in 360 degrees. I see a right triangle. Anytime I see a right triangle, the ghost of Pythagoras comes out of the wall and speaks to me. Hi, Pythagoras. How you doing down there? Oh, no, not down there. That's Hades. Hopefully you're up there talking to, you know, the big guys, Jupiter and all those guys. Oh, sorry. That's cosine squared x. Because obviously this is cosine x. If that's cosine squared x, then this is sine squared x. And this is still 1. Ha! 1 minus cosine squared x. 1 minus cosine squared x equals sine squared x. My God, that seems to be true. So this is sine squared x times cosecant. Well, let's see, we were talking about the, oh, that's the reciprocal of sine. Ah, this must mean that sine squared x is sine x times sine x. Well, I know what that is. That's 1. So this thing was equal to sine x. All right, let's play with one. Let's play with one here. A 3, 4, 5 triangle. All right, let's play with a 3, 4, 5 triangle. We'll make that the 3, that the 4. 3, 4, 5. We know that to be a right triangle. Let's do 1 minus cosine squared x. Well, cosine squared x is 3/5. So I'm doing 1 minus 3/5 squared. And that's in parentheses. Times cosecant. Cosecant is reciprocal of cosine. So that's 5/3. Let's actually do this out. So this is 1 minus 9/25 times 5/3. I haven't done any straight math like this in a long time, huh? So 1 minus 9/25, well, this is 25/25. So that's 16/25 times 5/3. I don't like this. I did something wrong. Gonna have to go back and do it all over again. Let me write it here. 1 minus cosine squared x times cosecant squared x. Yeah, I made that mistake, right? It's 5/3, it's not 5/3. Cosecant is reciprocal of sine, which is 5/4. All right, talking about cosine and cosecant got me all followed up there. Now, something very important happened. All right, I was able to recognize that I made a mistake. Why did I make a mistake? Because I did this problem from 2 perspectives. I knew the outcome was supposed to be sine squared, and it wasn't. That meant I either did something wrong with the identity, or I did something wrong with this calculation. That happens in math all the time. It is one of the most important things that you can learn, that if you want to make sure that a problem is right, do it 2 different ways. If you only do it one way, you're liable to make the same careless error that you did the first time. Okay, so I didn't come up with that. I listened to a Harvard professor talk about that. He's absolutely right. And so different perspectives are important. So let's look at this now. So 4 goes into 16. I think you're still seeing this sort of. Yes, okay. So I'll put my answer here so you can see it. So 4 goes into 16 4 times, 5 goes into 25 5, and I get 4 over 5. Oh, well, what is that? Oh, that's the sine ratio, opposite over hypotenuse, which is what we got a little while ago. Okay. I have to keep looking at the length of time on this video. Sometimes Zoom only gives you a certain number of minutes of the recording. At least that was the case. So now we're going to switch gears. I like switching gears. Here, you're given this information. A equals 35. A equals 8, B equals 9. A equals 8 and B equals 9. We're going to solve this triangle. Now solving this triangle, no, actually we're just looking for C. And we're looking for C. And this is going to be tough for you because you haven't had much practice with this. Okay, but first off, when you look at a triangle, the question is it a right triangle? Certainly no information there that says it is. So if you don't have a right angle, if you're not sure that you have a right angle, we're not going to use right triangle trig. We're going to use either law of sines or law of cosines. Law of sines. Law of sines is as follows. Little a compares to the sine of big A, the same way that little b compares to the sine of big C, equals little c compares to the sine of big C. And I encourage you to get online and read about that a little bit. Okay? Just take some time to just read a page about law of sines and law of cosines. All right, law of cosines is a little more, it's a little more difficult to deal with. Okay, so I'm going to talk about this one first. All right, so because I have this relationship, I have a big A and a little a, I have knowledge of that, I know I'm going to use law of sines. If this had been angle C, then I don't have a big C to little c, I have to use law of cosines, which will probably be the next problem. So right now I'm going to use law of sines. Okay, so what do I want to write? Well, I know 8, right? Well, I do this a little differently. So let me do what I like to do. I'm trying to find, I forgot what I'm trying to find. I'm trying to find C. Okay, so C, I don't have C. So let's see. So this is a typo. I should have said solve for big B. So this was a typo. I'll have to change that. I'm going to change that right now. All right, so there we go, big B. All right, otherwise it's a more lengthy problem to do. So law of sines says I'm trying to find big B, which is an angle, right? So I am going to do the reciprocal. Why did I write C? I'm trying to hurry, that's why. All right, so I am going to put sine of B, can you see that? Yes, in the numerator of the first fraction. It's just mechanically easier to do. So the sine of B, that's what my unknown is. I always put my unknown in the numerator of the first fraction. The sine of B compares to 9 the same way that the sine of 35 degrees compares to 8. I think I've talked about capital letters representing angles. I'll put a degree symbol there. And little letters, side lengths. Okay? So I'm going to erase this and do the work moving this way so you can see it. So we have 8 times the sine of B. Oh, I don't want to move that. I'm sorry. I'm talking too fast here. So I can isolate the sine of B by simply multiplying that fraction by 9. And it's good to get a feeling for size. All right, now I'm not going to get a great approximation here, but I do know the sine of 30 is a half. I know the sine of 30 is a half. I'll say 0.5. And I know the sine of 45 is 0.71. 35 is a little closer to this angle, and of course you're in a circle, it's not a linear relationship. but I'm somewhere in between this. Why don't we just say 0.6? Go to a calculator. I won't right now because I'm afraid I'm going to make a mess of something. So 0.6, what's 0.6 times 9? Well, 5.4. So 5.4 over 8, 6/8. We know 6/8 is 3/4, 0.75. 5/8, not so sure. 4/8, a half. So somewhere between a half and 0.75. So I just playing around. I want to make sure that folks understand that you can, if you're not in the morning without your first cup of coffee, you can get some educated guesses as to what you're going to get for an answer. But we're going to go to a calculator with this. Maybe I can have one of those on screen, get a little better at manipulating here so I don't lose the video, and actually do the sine of 35 and do this out. So how do I isolate B? That's the next challenge. Well, how have we isolated it so far? We've been using inverse operations. So we do the inverse operation of, that number, which is, I forget, 5 point something over 8. But it's exact when we write it 9 sine 35 degrees over 8. And that's an example of law sines. Okay. So where is that on the arc sine? Where is that number on the arc sine? We said something between 0.5 and 0.7. I think that was as well. This goes up to 1. That's 0. So we'd be in this vicinity here. And we'd have a triangle that would look something like that, and it's giving me that angle. I encourage you to find that angle while the video is paused, okay? That took a little time. I'm not going to do law of cosines. I'm going to do that separately with you when I have you in front of me face to face, okay? Because that takes a little bit of time. Now, we don't want to forget our skills from the past, okay? So you should be able to write the equation of a line in under 10 seconds. 9 gets you 5. I actually like writing it in the table. 9 gets you 5, 15 gets you 4, 15 gets you 4. You go ahead and do it. So we got x minus 9 plus 5. I guess we take that. We got to change the 6, and we go down 1. Okay? And put a y equals. All right, so we don't want to lose those skills. All right. Absolute value, 110, and passes through 538. Absolute value, 1 comma 10 through 5 comma 38. I guess that's easier to do. All right, so 1 comma 10, absolute value, x minus 1 plus 10. And then we got the absolute value of what? 5 minus 1. All right, so obviously 4. Right, and 10 to 38 is up 28, and you can reduce that fraction. All right, that should be familiar to you. So what was absolute value? Absolute value is, there's the graph of y equals x. When I slap that with an absolute value, what happens when I get a sign change? These negatives become what? Positives, and that's why we have that V-shaped graph. Okay, so if I gave you y equals 2 times the absolute value of x minus 3 plus 4, where does the sign change happen? At x equals 3. All right, so at x equals 3, we know we're at 4. There's 3, 4. And this is the slope of the linear parts. So this would be coming down at 2 to 1, and that would go up at 2 to 1. And you start to get your trajectory, numerical trajectories that you can manipulate and study. All right, just a little layering of absolute value. Square root function, 1879. So that's the endpoint, 1879 for square root. So we got the square root of x minus 18 plus 79. And we're going to go to an x value of 20. So if we go to x value of 20, it looks like we have changed this number by root 2. And I wrote 3. So we changed it by root 2. And we don't want to change it by root 2 because we're trying to get to 15. We're trying to get from 79 to 15, which means we got to go down, what, 64? Okay, so we would have had 1879 might have been here. We're going to go to 2015, which is maybe here. So that's what your graph would look like. All right, the trajectory, numerical trajectory would have taken on that form. What happens? We get a sign change at 18. At 18, we get a sign change. And to the left of the number 18, I have negatives. What's wrong with the square root of negatives? They're imaginary. And René Descartes had a great imagination, but not on his coordinate system. X's and Y's were positive. Right, René? Yeah, he's up there with Pythagoras. All right, here we go. Yeah. Famous philosopher. Yep, famous philosopher. Yep. Story has it that he proved that he existed because he could think. He said, I think, therefore I am. I think, therefore I am. And then he was going down the street and some kids were selling some lemonade. And they said, hey, René, you want a drink? And he said, I think not. He disappeared. Yeah. Name that tune. Oh, I love Name That Tune. A chance to look at some numerical trajectory. 0, 100, 3, 50. I don't think I'm going to do 25 problems here. I think I'm going to cut this off pretty soon. I think you got enough things to think about. 625, 9, 12.5. Everything in mathematics is looking for patterns, right? I got a feeling they're looking for patterns in that COVID critter, patterns that will destroy it. Okay, so start looking for patterns. Maybe you'll be the next Dr. Fauci. All right. So what do we got here? These are, that's pretty consistent on the left, huh? Jumping by threes. Remember, you're pausing this, right? Then playing this. Yeah, so it looks like every 3, something happens over here on the right side. Looks like these numbers cut in half. Yeah, geez, I wonder what that graph would look like. 0, 100. Let's just take a peek. 0, 100. 0, 100. Yeah, 350. So this, we'll do the tip of the marker being 3. So 350, that's half. Then another 3, 25. Then another 3, 12.5. Boy, this is what I got so far. Yeah, I got a feeling it's 6, what is this one? 5.75? 6.125. I think. Yeah, 6 point. My brain is very slow today. Half of 5. Half of 5. Oh my God. How can this be so hard for the old guy? Not even going to try. Too tired. Got to get more sleep. All right, so what do we got here? We got here. I'm upset with myself here. Half of 5. Can't believe I've got to do this, but I got to do it. 2 times 2 is 4. 1, 10.25. Oh my God, am I out of it? Oh God. Why? Okay. Anyway. I see. Starting with 100. That's a good starting amount. We'll call it the initial amount. We got a nice 0 here. Initial amount, 100. Looks like I'm cutting in half. That makes 50. Well, looks like I got to cut that in half again. That makes 25. Looks like I got to cut it in half again. That makes 12.5. Well, this looks like I'm doing 1/2 times 1/2 times 1. Oh, that reminds me of an exponential function. But when I put a 3 in, I get 1/8 times 100, and that's not 50. So I guess I got to make that 3 act like a 1. I got to make that 3 act like a 1. So, what can I do to the number 3? I could subtract 2. That makes it a 1. Yeah. Well, but 0 minus 2, that wrecks that. So I'm not going to do that. What's another way to make the number 3 act like a 1? Oh, this is change in x. Yeah, we've been doing change in x, operational change in x. I guess that's what goes there, change in x. Yeah, I think we've got it. This will open up the concept of a limit. So what's the limit? What's this thing going down to? If you keep cutting it in half. Keep cutting in half, like the end of this video. So you cut that in half. Ooh, I'm gone. And then you cut that in half. I'm gone. You know what? I'm melting. Goes to 0. So this graph, exponential decay, y equals 0, asymptotic behavior. Okay. The y values are not changing. when we get up to big X values, right? If you cut the number 1/2, the number 100 in half, let's do it 500 times. You go ahead, put that in the calculator, see what number you get. You're going to get 0.0 something small, okay? And if you did it 501 times, visually, you're not going to be able to see the Y value change. It's just going down. This concept is kind of like walking to a wall. Cut your distance in half every 3 seconds. Cut it in half every 3 seconds. I'll bring my finger to you. I'll cut it in half every 3, the distance from my finger to the screen. That's halfway. That's halfway. Halfway. Oh boy, this is hard to do. I still haven't touched the screen. That was a bad example. I don't know what that was, but anyway. So you guys, I hope you're doing well. I think that's a bit of a lesson. I think we exceeded a half an hour. I don't know how long that took us, but we got a few problems that we got to talk about. I hope you saw the inequality video. I would like to make a video on inequalities and layer some discussion. All right, it was just a preliminary homework, the last one. And this is a preliminary start, just keeping some of the old problems and new problems coming your way. All right, so in lieu of your internet difficulties, at some point, if your internet's working, I hope you can get in the classroom and work along with me, okay? And as I learn a little bit more about how to upload these things and use my screen, hopefully I can get some of those sine of 38 degrees quickly and easily. Maybe you can solve that there and do that yourselves, but it should be part of our instruction that the sine of 38 degrees is a little fraction between 1 and -1. Okay, and then we work with it. All right, so all is well. I'm still going to be checking to see if your net works at 10:30. If it does, we'll be having a class. My battery's dying, so I got to charge up. So I'm going to end the meeting and say goodbye. Goodbye.